it's the same one. Yeah. They all are. Perfect. Yeah. Okay. Welcome in the afternoon. Um, Now the next lecture is an introduction on biofuels, on transportation biofuels, and the question how to come from the different raw materials to something you can use as a for providing transportation service. So at least we have seen there are so many different types of biomass available, and you have to transform them at least finally to be used in an internal combustion engine. And there's at least a relatively long list of different biofuels. You can use pure vegetable oil in a combustion engine, but in most of the cases you produce a biodiesel by transesterification to fatty ethyl methyl ester, so it's biodiesel. You can also hydrate the vegetable oil to hydrated vegetable oil. It's called HVO. It's an upcoming fuel, not only in Europe but also here in Asia. Then, of course, bioethanol. I think you're quite familiar already with bioethanol. And then there's a long list of different so-called synthetic fuels. At least they all start when you convert the biomass to a carbon and hydrogen molecule, so to say. You're able to recombine it to different different synthetic fuels. And then there is biomethane, mainly coming from biogas production, and then upgrading it to biomethane. So these are the six most relevant fuels relevant today, but also being developed in future. And then there's a still longer list of many other biofuels under development. You can use pyrolysis oil, you can use high temperature fuels, all dedicated for very special feedstocks. At least, but when you look on the list of biofuels, we have two different types of combustion engine. We have the Otto engine and we have the diesel engine, and not all biofuel is suitable for both. At least each biofuel is suitable either for the Otto engine or for the diesel engine. And at least most of the biofuels you will see later on are currently used as blending. So you blend up gasoline, you blend up diesel to E10, E5, or B7 or B20. That's the big commercial use of biofuels today. And you see that it's mainly the biodiesel, the hydrated vegetable oil, and the so-called Fischer-Tropsch diesel. They are typically, or they can only be used in diesel engines, whereas the bioethanol, the biomethane, they are mainly dedicated to Otto fuel, to an Otto engine. That's the Fischer-Tropsch diesel. I don't know if you heard the name of Fischer-Tropsch before. I will explain later on, but it's a diesel quality. But it's a process where you gasify the biomass, at least to the carbon and the hydrogen molecule, and then recombine it to a diesel. And this process was developed in Germany by Mr. Fischer and Mr. Tropsch. And so it's called a Fischer-Tropsch diesel. And this technology was used on the end of Second World War, when they were running out of petrol. They can convert coal to petrol and gasoline. And then traditionally today, this is used also in South Africa still, because they have so much coal there, where they convert the coal to a diesel and gasoline quality. I don't think in India you have this process, but I don't know. But it's at least it was developed by Mr. Fischer and Mr. Tropsch. And it's also at least a possibility to convert solid biomass also to a diesel quality. Forest. Of course, there are two types of forest. Normally, you don't use the big stems, because the big stems are used for furnitures and for other and construction material, but all the leftovers. Yeah, so parts that the bark and the smaller parts and the branches, and also the very thin ones, they are very well dedicated on one hand for the pulp and paper industry, but also for the energy sector. Yeah, so in forestry, you have a possibility. And then in the trade and industry sector, very often biogenic residues occur from different production processes. It could be bark, it could be cooking oil. Yeah, in Europe we are collecting cooking oil quite a lot. Yeah, because if you collect that, you can convert it to biodiesel. And this is at least a biogenic source in the trade and industry sector, which is available. But as it is a residue, it is always coming in an amount depending on the main product they are doing. Yeah? So the more French fries you eat, the more waste cooking oil you come up. Yeah? Or in Austria, we like Wiener Schnitzel. I don't know if you know Wiener Schnitzel. Yeah? You also need oil made meat. Yeah? That's very typical for Austria. And this oil then can be used for biofuels, but it's at least it depends on how many French fries or Wiener Schnitzel you eat. Then you have more, so you cannot increase it because it's just an amount available. And the last thing is this so-called aquaculture. It's mainly about algae and seaweed, but it's mainly algae. They are growing in these artificial systems, these algae. So they are growing in water, and you have to put in, they must be heated and all the fertilizer. And the idea is they do photosynthesis, and they're growing, and they're also containing oil or starch or even sugars. But this is still a developing process, because all these systems you see here, they still need more energy to operate the system in pumping the water and putting in the nutrients compared the energy you get out. Yeah? So that the relation is not an energy producing system at the moment. But some people hope that the algae, because they have a very high theoretical potential per square meter or per hectare, yeah? Because if you really feed this organism quite well, they have the ability to really grow fast and provide big amounts of biomass, but still they are under development and not yet commercially available. So if you once have the biomass, of course, you have to convert it to an energy carrier. And there are many different conversion processes available. And at least you can separate them in three main groups. One is the biochemical one. So this means a biochemical conversion, which is mainly aerobic, or you can also call it alcohol fermentation. I think you're familiar with that. Or you can do it anaerobically. Yeah. So on one hand, you get an alcohol and an animal feed in most of the cases. In the other case, you use biogas, which is mainly used for wet material. It's manure, it's dung. You can convert into biogas, and you then get an energy carrier, the biogas, but you also get an upgraded fertilizer. So the leftover, the digested material has a very good fertilizing quality because you have a reduced carbon content, and that is very well being applied as a fertilizer in agriculture. So these are the main biochemical conversions. For the alcohol fermentation, I think you always need a sugar, and the sugar can be made directly if you have sugar from sugar beet or sugar cane, or you have to convert starch into sugar. But in future you can also convert cellulose via enzymes to sugars. So you have a broad spectrum of different raw materials, but still you need a sugar to be fermented. The second group means thermochemical. Thermo means you need temperature, at least temperature and heat, and you see that here in in the middle you put in the biomass, and if we heat it up to 800, 900 degree, the biomass starts to decompose, and first it melts, so first it becomes a liquid, and if you further heat it up, it becomes gaseous, and then you can create at least a product gas. And if you upgrade it further and separate the different particles and also other components, at least ending up with a pure carbon monoxide and hydrogen. So this is called the synthesis gas, which was also the process Mr. Fischer and Mr. Tropsch developed. Because of these two molecules, you're again able to produce all different types of fuels, diesel quality, gasoline quality, but also raw materials for the chemical industry. This is the thermochemical process. And the last is the physical or chemical or even pure mechanical processes. So if you convert the rapeseed to rape oil, you just have to press it and you get the cake and the oil. This is relatively simple. But then converting the oil into biodiesel, this is the transesterification process where you put in some alcohol. Normally it's methanol, yeah, and you mix it at a relative low temperature, and then it converts into biodiesel and glycerin. Yeah. The biodiesel can be used as a replacement for diesel, and the glycerin is a very valuable raw material for the chemical industry, for the pharmaceutical industry. They need glycerin, so this is then really a biogenic-based chemicals being used for other purposes. And at least, as I've mentioned before, all of these processes are core processes in these biorefineries, because you always produce a broader portfolio of different products, and these are the conversion processes. This is a big table. This is at least the list of biofuels I've shown you before. This is the list of raw materials, yeah, from agriculture, forestry, trade, industry, and aquaculture. And in between, you have these different conversion processes. Yeah? So you can imagine long list of raw materials, long list of conversion processes, long list of biofuels. And there are many different combinations possible from raw material to a biofuel. So you can have one raw material and make different biofuels, but you can have one biofuel made from different raw materials and vice versa. So there are really many different combinations. So far we have, I would say, about 5 key conversion processes for bioethanol, biodiesel, and hydrated vegetable oil using oil source, sugar sources, and starch sources. These are the key raw materials today. But the list for future combinations is quite long, and there are many things ongoing in conversion processes to different materials, because the demand for renewable fuels, for biofuels, is quite big. Yeah, you've seen globally we would need a very high amount. So the more we really can convert with new processes, new raw materials into a liquid or gaseous energy carrier, that is quite good. And this is a very busy table. It at least summarizes a little bit for the different, for biodiesel, bioethanol, biomethane, and synthetic biofuels, highlights the most relevant characteristics and combinations from raw material to a biofuel. And for biodiesel, you always have to start with fat or oil. Yeah, this is the starting point to do something further on. For bioethanol, you need the sugar coming from sugar directly from starch plants, or also from lignocellulosic plants in future. Whereas biomethane is mainly dedicated for wet or wetter material. Via this anaerobic digestion, you go to the biogas. The biogas is a combination of CO2 and methane, and only the methane is the thing you can use. So if you want to use it in a compressed natural gas car, I've seen you have many cars driving on compressed natural gas. There you have to upgrade the biogas to biomethane, yeah, which just means to separate the CO2. Yeah, so you have to get rid of the CO2, and then you have pure methane, and that can be used as a direct substitute for conventional fossil natural gas. Very relevant is, especially for biodiesel and bioethanol, that the heating value per liter is lower than for gasoline and diesel. The reason is that in the chemical specification of diesel and ethanol, you have still oxygen in it, which is part of the chemistry, but gives you no heating value. So at least this is relevant on one hand on the price, because very often people compare the economics per liter, but if you get less energy for bioethanol, you get 30% less energy compared to gasoline, so you have to be careful if you talk especially on prices, that you maybe it's cheaper per liter, but you also get less energy per liter. And also in other circumstances, in statistics or in applications, you really have to be aware what is the real heating value of the biomass for its specific application. In principle, it's so that a conventional diesel car can use a blending of biodiesel up to 10, maximum 20 volume% of biodiesel. Otherwise, these sophisticated engines don't work properly, because then they make more emissions. If you want really a pure biodiesel engine, you still have to change the engine a little bit. So at least the big application of biodiesel nowadays is really to go in blending, because all of the diesel cars accept the blending up to 10% already, and 10% with this big volume still is a big market to introduce or to use biofuels. For the ethanol, it's quite similar, and most of the cars, the new cars, they all are able to run on E10. That means 10% of ethanol blended, and you need a special vehicle, a so-called flexi-fuel vehicle, which is then able to also use ethanol up to 85%, by modification a little bit of the engine, but a pure bioethanol car is not developed yet. It will work, of course, but it specifically has to be developed. And for the biomethane, it's easy, because the biomethane chemically is the same as natural gas. So if you run your car on natural gas, you can also run it on 100% biomethane. So this is at least the same. This is again showing a similar picture coming from feedstock to different products. This time the products are differentiated between liquids and gaseous. In transportation sector, the liquids are so convenient, because a liquid is so easy to handle. So the gaseous fuel in Austria, for example, we have very less compressed natural gas car, which is not a big market at all. So we mainly drive on liquid fuels. And of course, it always competes a little bit with heat and power, because all of these feedstocks can also be directly used to produce electricity and heat. So this is also a possibility, but we will see later on that in most of these processes on making biofuels, you always produce also a certain amounts of electricity and heat that can also be used in this broader portfolio of biomass conversion. And now I'm going to show you the three most relevant value chains from raw material to a transportation fuel, and the most relevant byproducts, and they're at least summarized in three value chains. We call them value chain because we want to create value out of it, which is of course in one hand energy value, to get energy product as one value, but on the other hand also creating economic value, because all these systems only work in reality if the economy also works, if the costs and the revenues you get and the markets are available. So value chain really means it's also an economic incentive to do that. Otherwise, it's not so easy, or even not possible. So the first value chain is the oil and fat-based value chain. So at least they always start with oil and the fat. So oil and fat is, I hope you know the difference. It's at least the same chemical thing. One is liquid at room temperature and the other one is solid, but at least it's the same. And you start with an oil producing plant. So this surrounding here is a good example for an oil producing area. So also this is oil. And this oil, in the first step, you go into the pressing, which is a relatively simple process, but a very relevant process, because you produce the oil. and the pressed cake is a very good protein content, and you can use that as animal feed, for example. Yeah, so you can produce animal feed co-producing with raw oil. In where I come from in Styria, we like to eat our salad with pumpkin oil. I don't know if you've ever seen that. It's a dark green liquid. It looks a little bit like raw oil, but it's really tasteful because we have the pumpkin seeds and we press them, and the oil is a speciality, and the other fraction is a good animal feed for the animals we are housing. So it's also a good traditionally in our province we have this. So this is also a kind of value oil and fat-based value chain, but it ends at the salad. It ends at the table and not in the tank. What you see here is at least you then get the raw oil, and then the raw oil you need a little bit conditioning and refining to enter two different routes. One route is the transesterification route, where you add at least methanol or ethanol. You mix it at, I think, 60 or 70 degrees, and after a certain time, you get the biodiesel and the glycerin fraction. Yeah, and the glycerin is used as a byproduct, and the other one is the biodiesel or fatty ethyl methyl ester. The biodiesel was the traditional wording of it, but now more and more people talk about FAME or FAME, but it's chemically it's the same. And normally you can do the biodiesel, you can do in small facilities. So the process is at low temperature, at low pressure. So at least it's a relatively simple process. You can really make decentralized units. And this process, I have an additional slide on it. This process was developed in Graz, where I come from. It was in the beginning of the 90s. Where they have developed the chemistry, how to convert vegetable oil to a diesel quality. And then in Graz, they also developed this application I will show you later on. So it's a relatively simple process, so to say. If you see the second process here using hydrogen, for the hydrated vegetable oil, you need this hydrotreatment. So you need the hydrogen to get rid of the oxygen in the vegetable oil, yeah? And this can only be done on a bigger scale. Normally these processes are integrated in an oil refinery because there you have good sources of hydrogen, and with this hydrogen you can make big amounts of this HVO, and there are 2 or 3 big plants globally that really making big amounts of the HVO, and the quality of the HVO is really identically to the diesel because there's no oxygen in there anymore. So the HVO really has a perfect quality. And with the HVO, you can drive a diesel engine by 100%. This is the big advantage. Whereas for the biodiesel, you are limited by the properties because you still have oxygen and other things in there that do not fully be equal to the diesel. And it also has a 10% lower heating value than conventional diesel. Yeah, and you see here, so oil and fat is the starting point. You get 2 transportation fuels, the biodiesel and the hydrated vegetable oil, and you get different byproducts, yeah, from animal feed, but also chemical, pharmaceutical chemicals. The second value chain is the biochemical value chain, and it's called biochemical because the core process of this value chain is the fermentation. So the fermentation is in the center of this value chain, and you always need a sugar to go in there, and at least the raw materials are the sugar crops, the starch crops, and in future and also today on the pilot scale, these lignocellulosic materials, which are the main relevant is really wood and straw as the main big sources of lignocellulosic materials, where the cellulose and the hemicellulose can be converted to sugars, and that works all via enzymes, yeah, like we have in our mouth. These enzymes, they're similar to the ones you need to convert the starch into sugars, and then you have the yeast and you make the alcohol. A big difference is always the alcohol concentration you get after fermentation from the different feedstocks. And of course, the higher it is, the less water you have to evaporate afterwards to get really 100% alcohol. Yeah? But only the 100% alcohol is applicable to an engine. And And so from environmental perspective, as you need a heat source to evaporate all the water, it's always a big question, where is the water, not the water, where is the energy coming from to evaporate the water that influences the balance totally. And the leftovers from the fermentation, of course, that is a very good animal feed in most of the cases, yeah. And you can further upgrade it also to other materials. If you come from lignocellulosic material, the lignin cannot be converted to ethanol, yeah? But the lignin remains on the very end. It can also be a solid fuel, or it can be used as an energy carrier, yeah? It's the same like in pulp and paper industry. They only use the cellulose for the paper, and the lignin is used to provide the energy, electricity and heat to run the pulping process. And of course, when you have the alcohol here, there are different alcohol products and different alcohols being available that can be upgraded on one hand to transportation fuels, but also to other alcohols being used by the chemical industry. So this is the biochemical value chain with the core process, the fermentation, which has at least many possibilities in using biomass for transportation fuels. And the last one is the thermochemical value chain, because the thermochemical processing of biomass is the core process. You find here it's the gasification in the middle, yeah, where you gasify the wood or the lignocellulosic material, but it will be mainly wood or other solid leftovers like kernels, but also straw and others. Sometimes you have to pre-treat the material before you can put it in the gasifier. And in the gasifier, on one hand, you add heat, and on the other hand, you need most of the time oxygen or steam to make the gasification happen, that you have the real chemistry there, to at least to get the product, the raw gas, at least to get the synthesis gas. So the main idea in all this, in this thermochemical conversion, is at least to get again the CO and hydrogen gas, which is a syngas, and that can be further be used to different chemicals, but also different energy carriers. And the difference is only the temperature, the catalyst, and the pressure. Yeah, depending on which pressure, which catalyst and temperature you apply, you can get methane, you can get gasoline, you can get jet fuel, you can get many different products, and it's quite similar what's happening in a conventional oil refinery in the portfolio of processes you get. And this is at least the key reason why this is so relevant, this process, because you can really substitute conventional raw oil products with biomass-based raw materials, and this is at least the key driver for the relevance of this process. So we have at least these three key value chains with specific raw materials and specific final products that are relevant or most relevant in the area of biorefining biomass. This is the picture I wanted to show to you, the biodiesel development that happened in Austria in the 1990s. It was developed at university in a laboratory. Yeah, first they tried to do it in a laboratory, and as this was successful, they produced it first liters and tested if you can apply it in a vehicle. Yeah, and this worked very well, and this was a very good cooperation in Graz. We have different universities, and they cooperated on that. And then they found a farmer organization close to Graz, where they started to grow rapeseed. Yeah, they grow rapeseed, and they use the animal fat, because animal feed from the pressing, because there were many pig farms around. So this was one advantage, and the oil was then transesterified, and then the diesel was used first only in the tractors in the farms, yeah, and later on, as the volumes became bigger, they also converted the bus fleet in Graz, these green buses, they converted to biodiesel. And as it was such a big success, they were running out of rapeseed, so they also started to collect waste cooking oil, and there was a system introduced in the city of Graz to collect all the waste cooking oil. Yeah? You need a certain logistic. Yeah? You first start with the big producers, but then also go to the households to collect the waste cooking oil. This was a very good source. And finally, it worked that we collected the waste cooking oil in Graz, then converted it nearby and brought the diesel back to feed our bus fleet. Yeah? And this was a very successful activity starting in Graz. And then now we have a big company called BDI. They now produce these biodiesel producing plants globally. Yeah? Because it's, even if the technology is not so sophisticated, you need somebody who is able to do that. And this BDI is now an industrial company building biodiesel plants all over the world. And this is at least a very nice success story from laboratory development via testing, via piloting, finding a pilot area, and then making an industrial and economic success out of this. And this is something we in Graz are really proud of. And I was the first one making a life cycle assessment of this biodiesel being produced. I did it already at university for my master thesis. Yeah. This was the topic to analyze the greenhouse gas balance of making biodiesel. At this time, it was beginning of the 90s, I did my first LCA, and the results are still valid today. Yeah? So my calculation was not so bad, even we know much more today about these processes than we knew in the past, but still the orders of magnitudes on greenhouse gas saving it was, and when you use rapeseed oil, it's roughly 60% less greenhouse gases. If you use waste cooking oil, it's more than 90% greenhouse gas saving, and at least that was also part of my personal activity. Thank you very much. And that was at least really the starting point for me to step into that area. Yeah? And even at university with life cycle assessment, I was some kind of exotic, yeah, because nobody did that at technical university before, and they told me, you're a mechanical engineer. And finally, when I made my big examinations with all the professors sitting there, and I presented my work on life cycle assessment of biodiesel and so on, and they were listening and said, that's really interesting what you do, Mr. Jungmeier. This LCA what? LCA, yeah. But we think this is too complicated. And maybe it's better in future you go in a traditional workplace for a mechanical engineer, go to the automotive industry or making power plants, but this LCA, I don't think this will. So this was the recommendation when I left university, but I was so fascinating of this area, and then I had the opportunity to start at Ioneum Research already at this time, and there I really had the possibility to develop this methodology further on with academic cooperation and with industry cooperation, and I had then the opportunity also to make my PhD out of this activity, and this is what was quite nice, and really started with these biodiesel activities we had at the beginning of the 90s in Graz. And today we have in Austria roughly 8, 9, 10% biofuels on the market. Yeah? So we really have introduced them. It happened, the introduction happened in Europe because there was a law by the European Union. They said we need more renewable energy in the transportation sector. This happened 15 years ago. It was a long process. You can imagine if 27, at this time, we were 20, I don't know how many countries you were in Europe, but it took a long time to bring all this country to the same goal, to say we want to have 10% renewable fuels in the year 2020. Yeah, that was at least a political wish, and then it was a political law. It was a regulation for all of the European countries, and then really the business started to develop because the processes were there for biodiesel and bioethanol, and now there was also a reason to do so. There were some subsidies and help and innovation funds to build up this industry, but it was really built up because it was a political will to have more renewables in the energy sector, and that really succeeded, and that's why we have roughly 10% renewable fuels now in Austria. The most relevant is biodiesel still from oil crops. with the co-product animal feed and chemicals, and we have also very much used cooking oil. So we really established a big collection of waste cooking oil all over Austria, and we spread this also to the neighboring countries, because you know Austria is in the center of Europe. So we also introduced these logistics in the neighboring countries, quite a good location. Hydrated vegetable oil we do not produce in Austria, not yet. Our oil refinery, they want to do it, but not yet. So we are importing this from I think in the Netherlands and in Finland. They have two big facilities. We have a little bit of biomethane mainly from maize and agricultural residues, but this is very, very little because we have no no cars running on compressed natural gas. And so we cannot bring it in the transportation sector. Normally the biomethane is injected in the natural gas grid and used for heat and power, but not in the transportation sector. And the second biggest thing we do in Austria is bioethanol. We have a very big bioethanol complex also on the river Danube, where we make at least conventional bioethanol. So they started with corn and wheat in the very beginning. And then they started to further develop a starch factory, a starch biorefinery, because out of starch you can make so many different other products. And they further used this and use only residue stream from the starch for ethanol production. And they also started to collect the CO2, which you normally don't use, but they started to collect the CO2 because there's a big market also for CO2. In the beverage market and for technical applications, so they also use the CO2 as a very valuable product. Secondly, we also make bioethanol from black liquor. Black liquor is the remaining part in the pulp and paper industry which you cannot convert to paper. But in some specific processes, they also have sugars in this black liquor. And these sugars can be also converted to bioethanol. And we have one pulp and paper mill in Austria that converts the black liquor into bioethanol. And the remaining fraction still can be used to make electricity and heat. So the conventional way was only make electricity and heat. And now they first ferment it and then use it for electricity and heat, and they have a very good greenhouse gas balance. They have 98% less greenhouse gases than conventional gasoline. So 98% reduction because it's a residue stream out of a pulp mill. And I only believe this 98% because it was calculated by my colleagues and me. So we really know the details, so we can be really sure that it's really a greenhouse gas saving of 98%. At least the amount is limited because the amount of pulp they produce there is limited, so also the amount of ethanol they can make, but it has a very high market value in the meantime because everybody is looking for bioenergy carriers with a very high greenhouse gas saving. So this is at least common technology today, and we have some research activities on converting wood and straw into bioethanol, but this is still on in Austria at least at a very low level. We do more work and we build a very good testing facility on Fischer-Tropsch diesel, where we gasify wood and make this broad portfolio from chemicals and different fuels. So, but this is still in the research phase. So we are still researching and developing that and to further develop. So at least summarizing, biodiesel and bioethanol are the key biofuels we have nowadays in Austria. We nearly have in total, we are blending this to B7, 7 volumes percent in diesel, and E10, 10 volume percent in gasoline. That's the way we're entering the market. So the big question is always, what is the big benefit if you use biofuel in comparison to a fossil fuel? And with your background, you will be able to answer the first question: how much CO2 is emitted when you burn 1 liter of gasoline? Yeah. So did you ever think when you burn 1 liter of gasoline, how much CO2 you're going to create? Pardon? Pardon? is the main content of gasoline? It's carbon. Yeah? So if you burn one carbon molecule to CO2, it gets heavier. Yeah. How much heavier is it getting? From 12 to oxygen is 16. 12 is the carbon, and the CO2 is 44. Yeah. So the weight increases by a factor 3.6. Yeah. So if you roughly say 1 liter of gasoline is 1 kilogram, a little bit less, and you triple the weight, you get chemically or physically or chemically at least 3 kilograms. Yeah. So if you burn 1 liter of gasoline, you get 3 kilograms of CO2. And that's bad. That's bad. And the second question is, if you burn 1 kilogram of dry wood, yeah, how much CO2 do you get? You have 1 kilogram dry wood, so no water in it, so it's really the wood. And this chemical formula of wood, what is a key element in the chemical formula of wood? Yeah, but it's carbon, hydrogen, and oxygen. Yeah, okay. So if you have 1 kilogram of wood, roughly, how much is oxygen in that wood? It's roughly half of it. Yeah. So if you have a piece of wood, the half of it, you carry it home, 1 kilogram, but half of this kilogram has no heating value. Yeah. So you have to carry it, but it's only oxygen. Yeah? So this kilogram of wood only has half a kilogram of carbon. And if you burn half a kilogram of carbon by tripling or 3.6 the weight, you get roughly 1.5 kilograms. Yeah? So if you burn 1 kilogram of wood, you get 1.5 kilograms of CO2. And the molecule CO2 is the same for the gasoline and the wood. It's CO2. Chemically, it's the same. So the big question is, why is one better than the other? Yeah? And the reason is, if you use biogenic carbon, you're part of a natural carbon cycle. Yeah? So all our vegetation outside, they uptake CO2 from the atmosphere, and during night or when they die, they release again the CO2 in a natural cycle. So if you don't touch a forest or a field, more or less the carbon cycle is closed. Yeah? It also releases CO2 during the night, during winter. So this is the natural biogenic cycle. And if we now use the piece of wood for energy generation, yeah, we do the same thing. We just oxidize the carbon. We add oxygen, and we make the CO2. Yeah? And the only difference is that this happens very quick. Yeah? If you burn it, it disappears. Yeah? So it's also a question, how long does it take until the carbon cycle is really closed again? In agriculture, it's easier. If you have an agricultural field here, and you make an energy carrier like biodiesel or bioethanol with the raw material, after 1 year, when in agriculture the rape and the wheat is regrowing, at least the carbon cycle is closed within 1 year. Yeah? So for agriculture, it's the same for our food. All the food we eat, finally it ends up as CO2. Yeah? And that is always part of the biogenic carbon cycle, so there is no accumulation of CO2 in the atmosphere. Yeah? This is why this biogenic carbon is, so to say, the good carbon, because it's in the cycle mainly influenced that the photosynthesis is uptaking it. Yeah? And it becomes more difficult if this is in a forest. Normally in the forest, the trees takes you 80, 90, 100 years till they grow. Yeah? So it takes 100 years that the tree is grown. If you don't touch the tree, it falls down sooner or later, and it will disappear as CO2 after 20 or 30 years or however. Yeah, and then the cycle is closed. If we burn this tree, the whole CO2 which was accumulated in the last 100 years is emitted at one time in the atmosphere. Yeah? So it took us 100 years to collect it in the tree, but when we burn it, it's in the atmosphere, and it takes, when you replant it, it takes another 100 years that you have the carbon cycle closed again, or to have the carbon stored again in the tree. And this is the tricky thing, that when you use forestry biomass, that you might have an increase of CO2 in the atmosphere for a certain time, yeah, until it's again uptaken. And so in principle, for agriculture, it's closed in 1 year. And for forestry, it might take up to 100 years if you look only on one single tree. If you look on a whole forest, yeah, with young trees, old trees, big trees, small trees, depending on the relation how much you take out and use for energy, compared to what's still remaining in the forest, uptaking CO2, if this relation is in an equilibrium, yeah, then you have no CO2 accumulation in the atmosphere. And this is the tricky thing, not use more wood than is regrown in a certain area per year. Then you can be sure that the CO2 concentration remains stable in the atmosphere. Yeah? Because all these CO2 flows you see here, they are a function of time. And we don't want to have CO2 accumulating in the atmosphere. Yeah? So at least the emissions and the uptake must be in an equilibrium. And even for a country like Austria, where we have 45% of Austria are covered with forests, and we are very few people, we are only 8.5 million people, yeah? But at least we should not take more wood out of the forest that is regrown year by year. And this is a tricky balance, because the forest has younger forests, older forests. It's a big mixture also of different species. And this is really the tricky thing. To have a really sustainable biomass system means a sustainable forestry system. And the minimum criteria is always that you replant. Yeah? So if you cut down a forest, you must replant it again. Yeah? And you know, they start being like this and it takes a long time. But the replanting is very essential. If you just cut it down and use it, that's not sustainable at all. And this really needs a good, sustainable forestry management to have the possibility to keep this biogenic carbon cycle in a balance. And this was, when I was young, there was no discussion on that, because people said if you emit and it's recollected via photosynthesis, it must be zero sooner or later. Yeah? And I would say 20 years ago or 25 years ago, people start to think about it, and they found out it's much more complicated because of the different timing of the different processes to really make sure that the forestry biomass is sustainable. And additionally, it comes that, of course, the forest also store the carbon. Yeah? And if you make a chair or a table out of the carbon is still stored here. Yeah, so this is still a storage, and as long as the carbon is stored, you don't have a problem. The problem starts when you burn the chair to use the energy, then the CO2 ends in the atmosphere, and then you have to rethink, is it good or bad to burn wood? Yeah? And we were discussing if the old furnitures we inherit from our grandparents, very nice furnitures, yeah, if you burn them, it's bad for the environment because the CO2 was collected maybe 200 years in the past. Yeah? So and now you add it again in the atmosphere, so you have to regrow many trees at the same time. The main message of all this, with the forestry, it's very tricky to guarantee that the CO2 balance is closed. And in Europe, we have developed a very specific system to count the biogenic carbon emissions. It's also part of the national inventories of greenhouse gases, because each country, India, Austria, Europe, they all have to make annually a greenhouse gas balance. So they also have to count for the biogenic CO2, mainly reporting how much carbon is stored in the forests, and to see if there's more or less carbon stored in the forest, if this is really in balance with the amount of forest you use. So, and this is at least reported in the national inventories. So in the past, we did not report in LCAs on the biogenic carbon. We just said it's zero and forgot about it. But nowadays, it's also important to count for the biogenic carbon. Yeah? Even if you say it's first uptaken as a minus and then it's released as a plus and totally the carbon is zero, it's still important to now report also on the biogenic carbon flows and to further analyze if the system really is closed. And to really allow a closed carbon cycle, I mentioned the word certification already in the morning, it really needs a system that guarantees that the biomass you use is grown sustainably. Yeah? There's really a system in place now to avoid the risk of unsustainable biomass production. Yeah? That's why with the biomass also the LCA and all the environmental issues are much more complex, because you're always interacting with the biosphere and nature compared to hydropower or wind power, which is a pure technical thing, more or less, to really make sure that the carbon cycle is closed. Yeah? On a medium term and on a long term and on a short term, because we do not need additional carbon in the atmosphere, even if it comes from biogenic sources. Yeah? So and that is at least the big challenge for that, and this now in many areas in the pulp and paper sector, but also in the wood sector and in the energy sector, more and more certification is taking place, that at least each piece of wood needs somehow a certificate showing that it's replanted and coming from a sustainable management forest. And if the system works properly, of course, then it's really guaranteed that this has finally a good sustainability balance or greenhouse gas balance or other issues. And this was at least also a key driver when in Europe we started to introduce biofuels. And as I've mentioned before, 15 years ago, Europe wanted to have more renewable energy in the transportation sector. And this was the law, it's the Renewable Energy Directive. And it's a legal document. And you know, to read a legal document is not that interesting. So if you see that, you can look, the annex is the interesting of this legislative, because it's the first legislation document which needs an LCA approach in the annex, because it gives you a regulation for putting biofuels on the European market. And for each liter of biofuel, you need a life cycle assessment, stated by law, because already at this time in 2009, they knew that not each piece of biomass is sustainable per definition. No, it has to be certified, it has to be managed and calculated. And here in this Renewable Energy Directive, in the annex, you find the formula of the life cycle greenhouse gas emissions of a biofuel. Yeah? And so this was the second time I was happy in my career. Yeah, first, I was the first one being exotic at university making life cycle assessment. But 20 years later, life cycle assessment was part of a European regulation, because everybody realized that life cycle assessment is necessary to guarantee sustainable products, to guarantee that the biofuels reduce greenhouse gases. And they have been very clever at this time, because at this time you can imagine, because the farmers are involved, the industry is involved, everybody complained. Said, ooh, boo, that's so difficult, But they say, okay, we make it a little bit simpler. Yeah? So they simplified the approach a little bit. And then they said, it's easy for you because you have only to have a saving of 35% greenhouse gases compared to gasoline or diesel. And I said, bah, only 35%, this is not that much. Yeah? You build up a new industry and you're only saving 1/3 of emissions. I was a little bit annoyed, saying only 35%. But they have been clever, because they said in the beginning, it's 35%. After 5 years, it was 50%. Then it was 60%, and now it's 65%. So as once you have introduced the system, at this time, everybody was sure we can reach this saving. Yeah? To reach a saving of 30% is easier, but to reach a saving now of 65%, you need a good technical process. You need a good feedstock. So this was a very good idea to start with a low target on the beginning and increase the target. With new feedstocks and so on, they reach the target also nowadays, and the system is running all over Europe. And each liter of biofuel has an LCA with it. And if you buy it, you get a price and the greenhouse gas emission, because you have to make sure that each liter is used properly. Okay, another aspect besides greenhouse gases, about the competition, biofuels, as you've seen, can use raw materials that can be also used for other purposes. So it's also a question of land use, of land occupation. So how much hectares do you need for 1 kilometer or for one year or so on? And so the discussion started about land use. And to make a proper calculation on land use is a very tricky thing, so to say. And in this development, you've very often found graphs like this. Yeah? And they tell you that how many kilometers can you drive when you occupy 1 hectare per year. Yeah? And they compared the biodiesel made from rapeseed, ethanol from wheat, ethanol from wood, the synthetic diesel from wood, the synthetic diesel from black liquor from the pulp and paper industry, or the DME, dimethyl ester or methanol from wood and black liquor. Yeah? And they found out that the DME needs, you can drive the longest distance with a big truck per 1 hectare. And you see the biodiesel looks very poor. The bioethanol looks very poor. Yeah? And the big question is, could that be? Is it so simple? And then you say, okay, let's see. The wood grows in the forest. So the hectare must be 1 hectare forest. The wheat and the rape, they grew in agriculture. So the hectare is agricultural land. But there's a difference if you have a hectare of forestry or a hectare of agriculture. So a hectare is not a hectare. Yeah? So the first thing is, this is not fair because it's not the same hectare. Yeah? If you have a forest there or an agriculture there. But secondly, if you find here black liquor, I've never seen a black liquor tree in the forest, because black liquor is not growing in forest. It's a side product of the pulp and paper industry. So how can they allocate a hectare to a residue from the pulp and paper industry, which makes pulp and paper? So the question is, how much is from this hectare is going to the pulp? How much is going to the black liquor and so on? So this is at least not a fair comparison. And we know when you make biodiesel or ethanol, we always produce animal feed. So how did they count for the animal feed? Because on this hectare, due to the technical characteristics, yeah, when you make 1 ton of biodiesel, you make 2 tons of animal feed. Yeah, so on this 1 hectare, you have the double amount of animal feed, so you have to allocate somehow the hectare also to the animal feed. The same with the ethanol. When you make 1 ton of ethanol, you make 1 ton of animal feed. So it's a 1-to-1, more or less. Yeah? This is also not seen for that. Yeah? So the main message is, we will talk about land use change during the week. This comparison, really be fair, really be careful and see if it's really a fair comparison. And you can imagine who made this one. Yeah? It's a company. They make the DME and the methanol, yeah, and trying to say we are best, most efficient in land use. But as young scientists, yeah, here at the university, you really have to ask question: what is the hectare? How did you consider the byproducts? That's the important thing. Yeah? To ask questions, think about, and then say this is not a fair comparison. To be honest, to make a really fair comparison on that is a very complicated issue. Yeah, because you have so many products. From this, you start with a hectare, you make rapeseed, but then you make glycerin, biodiesel, and animal feed from the same hectare. And how can you say, okay, this part of the hectare, I give this to biodiesel, this I give to animal feed. You need to think how you do it in a robust scientific way, say how much of my hectare can be allocated to these three products. And this is not trivial. Yeah? This needs, and we will talk about allocation, and for land use, of course, it's very essential, and a thing like this is a little bit too simple, so to say, too simple. Okay, what is the current demand on biofuels? The current demand on biofuels globally, the big bioethanol production started in Brazil and in North America, because they wanted to get independent from raw oil imports. That was the key drivers in the 80s. It was not environmental protection, it was energy security. Yeah? Mainly in America and South and North America. To secure energy security, use own feedstock and make ethanol. That was developed in Brazil using sugarcane, and in North America using mainly corn. And Europe was a little bit late on that, but this is more or less the development of biofuels from 2016 up to today. So we are in the middle. This is today. And it's expected in future that it will slowly develop, as already a significant potential is already used from the different countries. And you see that the light blue is bioethanol. Yeah. This graph is in liters per year. Yeah? The ethanol has the highest share, and the dark blue is the biodiesel, and the light green is the renewable diesel, is this hydrated vegetable oil. You see, this is the smallest part so far. And in future, we expect also more advanced biofuels. But it's in liter. Yeah, and you know that if you do the same graph in energy units, in terajoule units, you will see that the ethanol is having 25% less energy than the biodiesel. Of course, then the relation would be in favor of biodiesel, but still the total amounts of biodiesel on the global market is less, or significantly less, compared to ethanol. And if we have such big amounts of biofuels on the market, it's also a question which are the leading countries in that area. And here in that graph, there's 3 time periods distinguished, and the orange-yellow part are the advanced economies, how they call it, which is mainly the United States. Europe was a front runner in the past, but in future it's expected that the other economies, the emerging economies, are speeding up and also developing. You see, India here is the light green one, and this is a graph from the International Energy Agency. So this is the expectation that India will produce significantly amounts of biofuels in the future. So it's very important for you to be familiar with this area, that you can make good life cycle assessments, and to guarantee that the future produced biofuels in your country really fulfill the necessary sustainability indicators. And the question is, if you make now a greenhouse gas balance of these biofuels, you will find here, this is the graph for bioethanol, and in comparison to petrol, in the average situation of all 27 European countries. In EU, it's different in each country, but this is the average so far. And you see here 2 things. One thing are the greenhouse gas emissions, given in grams CO2 equivalent per kilometer. So how much greenhouse gas emissions per kilometer do you have when you drive 1 kilometer? On the right-hand side, you see the primary energy demand, accumulated energy demand, which is a matrix for the energy efficiency. That means how much energy I have to take from nature to drive 1 kilometer. Yeah? So, and this is very important because the message from greenhouse gas emissions and primary energy is a little bit different. Yeah? Is the first message. And the second message is here, the lowest column here. This is pure gasoline, and up from is pure ethanol. Yeah? And in between we have the E5 and the E10 as a blending, as the average feedstock mix we have in Europe. And you see that the ethanol production, or the ethanol is roughly having 20% less greenhouse gas emission, not 250, roughly 200 grams. Yeah? So still, there is much greenhouse gas emitted when you make bioethanol. The main reason is that the ethanol production needs much energy for the distillation, and commercially in Europe, it's still mainly natural gas being used for that because it's the most economic way, not for environment, but for the economy. So therefore, they do not use the whole possibilities of ethanol. But secondly, this is a life cycle assessment per driven kilometer. Yeah? So also the vehicle itself, to make the vehicle and to dismantle the vehicle, is included in that calculation. Yeah? Because you have to build it, and we build a normal gasoline car until it ends in the car shop. It has already 10 tons of greenhouse gases emitted to build it. Yeah? And this is also considered here per kilometer via the lifetime mileage in the LCA. You will learn all the details. So this is a first taste of life cycle assessment and a result on greenhouse gas emissions. On the other side, you see the primary energy demand. Yeah? In the case of ethanol, the primary energy is the corn you get. Yeah? This is a starting point, the heating value of the corn. So how much heating value in the corn you need to drive 1 kilometer. Whereas for the petrol, the very first one, it's the raw oil. So how many megajoule of raw oil do you need to drive 1 kilometer? And you see the process of making ethanol needs the double amount of energy compared to raw oil, which is for some people in the very beginning a little bit astonishing. Yeah. Secondly, it needs some effort to make something liquid out of corn. Yeah. That's why you need to put energy mainly in the cultivation phase of the corn, but also in the distillation in the bioethanol production. Whereas when you pump up raw oil, everything is liquid and ready already. So nature has done most of the work for the fossil. Yeah? But still, it's significantly higher. But the main difference is that in the case of bioethanol, it's renewable energy. Yeah? And renewable energy, we know, is better than the fossil energy. So therefore, the maize is having more energy, but 90% is really renewable energy. And we will learn later on when we talk about an indicator of primary energy demand, you will learn about how necessary it is to distinguish between the fossil and the renewable part. I show you the same picture now for diesel and biodiesel. And normally the diesel cars are a little bit more efficient, so the values are a little bit lower, so it's a little bit above 200 grams per kilometer. And then we have the biodiesel, the B7, and then we have the pure HVO, the pure farmer, using the European raw material mix. So the reduction is roughly 25 to 50 grams, so the reduction is a little bit bigger than for the bioethanol. And the upper front one is for Fischer-Tropsch diesel, which is not commercially available, but if you use wood and convert it to Fischer-Tropsch, you have an emission significantly below 100 gram. And with the primary energy, it's the same. All the biofuels have a higher primary energy demand due to the conversion efforts compared to the fossil diesel, but still this type of energy is nearly 100% renewable. Also, very important message of this graph is, you see, I make a range for the results. So I don't give one single number. We made a range. Because we will learn when we talk about life cycle assessment, at least to end up with one value, if you calculate it, you get one value. But if you lean back a little bit and you see, okay, I'm interested in significant differences between two systems, and then you have to think, what is a reasonable range? If I change my assumptions a little bit to see if there's a significant difference, if one is here and one is here, you say, I'm sure this one has lower emissions than this. If it's something like this, you have to be honest saying, I'm not sure if there's a difference. Yeah? This is very important also in LCA to see what are significant differences. And the difference starts to be significant 10% and more. If it's only a 2 or 3%, that's not. It must really be significant. And if we have to reduce greenhouse gases by 80%, we're looking for systems that have significant reductions. So also in our consideration, we need to have significant differences. You can make the same calculation on greenhouse gas savings. I found this graph made from the International Energy Agency. They have many activities in the area of biofuels, and these are different countries. There is also India in there and other countries. And really depending on the feedstock and the baseline, you see how much the different energy, biodiesel and ethanol in average can save greenhouse gases. And here you see values between 40% up to nearly 80%, yeah, because depending on the feedstock. And here you also see this is South Africa. In South Africa, the baseline for South Africa, the diesel and gasoline for South Africa is so much higher because they make gasoline and diesel out of coal. And doing so, you have significantly, I would say, 60-70% more emission if you make from coal gasoline or diesel, or if you make it from raw oil. So this is at least the reason why there the biofuels even have a bigger saving. But the production is process, as I mentioned before. This is the Fischer-Tropsch process they apply here in South Africa. So I'm on the end of of this lecture by summarizing a little bit the take-home message for today. It's important to know there are many different types of biofuel, of transportation biofuels. Yeah? So you always have to be clear what is the transportation fuel you're analyzing. There are so many different raw materials, yeah? So you also have to know the different raw materials they are made from. They have different properties, they have different conversion processes, they have different criteria for sustainability, and in between there are many different conversion processes. Yeah? And when you talk about a biofuel, it's always important to really specify the raw material, the biofuel, and in most of the cases also necessary to specify the conversion process. And that will be what we will learn tomorrow when we talk about biorefinery, how to do that in a harmonized, in a common form, because it's so important that you always talk about the same thing when you talk and discuss with others. So you really have to be precise in specifying. Then we have seen there are 3 key value chains for biofuels. It's the oil and fat-based chain. Yeah, they use oil and fat chain. Then is the biochemical conversion, where the core process is the fermentation, for which you need the sugars. And the sugars can come directly from agriculture or from starch, or even in future or even today from cellulose and hemicellulose. And the third value chain is the thermochemical conversion, with the key process of gasification, where you make the synthesis gas exist being a combination of CO and hydrogen, and with these combinations you can make a broad variety of different products. We've also seen that a closed biogenic cycle is the key to have a sustainable biofuel, biomass, bioenergy system. You really have to see if the CO2 uptake from the atmosphere is nearly at the same time when you put back the CO2, the biogenic CO2 emissions when you drive your car, or if you burn the biomass, that this is really a closed cycle, and this is the key, and this is really still a challenge for the sustainability. Then we have seen that biodiesel and bioethanol are currently the most relevant commercial biofuels of today. They are made from oil, starch, and sugar crops. The hydrated vegetable oil is upcoming. It's a different process and globally not yet so relevant. I've also mentioned that biofuels in future made from lignocellulosic feedstock, because wood, and I would assume in this area the straw, is a very big available resource that can be used as a feedstock for biofuels, bioethanol, or even Fischer-Tropsch diesel. And finally, we have seen that a substantial greenhouse gas reduction is essential, and not of the systems per se give you a substantial reduction, so you really have to identify the framework conditions. This is still a challenge to maximize the greenhouse gas reduction, and of course an adequate land use. How to use the land, how to manage also the byproducts. These are key challenges for the further development and maintaining the biofuels. So this is the final slide of this lecture, and if you have any questions, now you can ask them in the big forum or afterwards also on a bilateral personal scale, however you like it.
Hello. Thank you very much for a wonderful talk related to biofuel production. So I have one doubt that one of the primary steps for production of biofuel from biomass is the pre-treatment. Right. Let's say if we consider from lignocellulose, if you want to produce bioethanol, we need to do the pre-treatment at the initial stage. So that pre-treatment step, can you comment on the sustainable methods for that pre-treatment? Conventionally, we have a chemical, thermochemical, or combination of them, or biochemical. But what are the current trending sustainable methods for the pre-treatment of lignocellulose material?
The sound was very bad, so I'm not sure if I understood your question quite well, because it's...
Okay. Sorry, what are the trending sustainable methods for lignocellulose pre-treatment? Pre-treatment? Yes.
I'm not sure if I can answer this question completely. I made several LCAs on pre-treatment methods. I cannot say per se which is the best one, because it really depends on the overall process. What are the different products you can make out of it? What are the amount of product streams? And also what is happening to the non-usable stream? Yeah? So it's in an LCA, it's just one out of the whole process. And normally, if you have different pre-treatment methodologies, you have different products. Yeah? And it might be that with one system you have 3 products, and with the other you have 4. And then you need a fair comparison of a system with 3 products and a system with 4 products. Yeah? And we will learn on that in detail, and maybe we can use this example in one of the interactive work in small groups we want to do, to see the different products and how to make a fair comparison. And finally, sustainable is a broad word. So if you look on greenhouse gases, maybe one is better. If you look on energy efficiency, the other one is better. So even we have to define what are the key environmental indicators we want to analyze, and then see which of the pretreatment is maybe better than another one. Yeah.
Okay, thank you. So because why I asked recently, there are a lot of papers related to ionic liquids or DP-Tech dissolvents. They claim that using these greener solvents, we can easily separate lignin and from the cellulose, then ferment the cellulose to produce the biofuel. So that is right now, I don't know. I still have a doubt about that. That's why I just wanted a clarity. Thank you.
But at least the lignin is a tricky thing because you can also make product out of lignin, yeah? Or you can use the lignin to make the energy for the processing. So you can't do both because you have the lignin only once, and this is also a tricky thing. Yeah? So even the lignin is part of the overall LCA, yeah? And then it even becomes more complicated. And in most of the papers, I know that the guys who are developing a certain process, and in most of the cases in LCA say this is maybe a good one. It's the most cheapest one in all the comparisons and maybe the most environmental one. But still on a scientific way, it's a very tricky thing to compare this, but we can exercise this and see what are the key aspects we have to consider in such LCA comparisons.
Thank you.
So thank you, sir. Thank you for such an enlightening talk. And I think those who are not earlier exposed to the field of bioethanol or biofuel, they are, becoming, familiar with the field, and it will, it will be better for them to, to read a few things in your hostel today, and just to clear some terms which our expert have discussed, so that you understand the concept and the future lectures in a better way. So anyway, so we had two nice talks by Professor Youngweir today, and we will continue with his talks tomorrow, and maybe we can have 5-minute break and then we will start the next lecture. Okay.